Hey guys, Alex here in the lab. So tell me if this has ever happened to you. You've gone online and you've ordered a new radio. So for example, I have like a Heltec V4 here, and it finally arrives in the mail. So you rip open the box, and the first thing you want to do is you want to flash, meshcore or meshtastic onto your radio. So you take the radio and you plug it into your computer, and the radio powers up, and then you think, oh no, I forgot to attach the antenna. And of course, if your radio transmits without the antenna attached, it can damage the radio. And now you're left wondering, if I just damage my new radio, you set it up and you see that you're not getting the performance that you expect. But is that the transmitter? Was it damaged, or is that your antenna isn't performing, or is it poor placement? This is a hard thing to diagnose if you don't have the right tools for it. And the right tools for it, the traditional way of doing a sort of diagnostic on the output power of your radio is you might use something like this is called a tiny spectrum analyzer, and it's a pocket-sized spectrum analyzer. And a spectrum analyzer will measure the output power on a slice of the spectrum and show you where the power is in the spectrums in the frequency domain. Or maybe you go and you buy a dedicated RF watt meter. So this is something that you might buy if you're you might already own if you're like a ham radio amateur. You can go on to DX Engineering or whatever the various ham radio outfitters, and you can go buy a dedicated watt meter. The thing that these two solutions have in common is that they're fairly expensive. So the tiny spectrum analyzer that I have, it's about $300, which is much cheaper than like a bench lab one, but still quite a bit of money. And if you go buy an RF power meter, from DX Engineering, from a reputable brand, those also cost a fair bit of money, and they sort of get more expensive the higher the frequency. So I looked briefly, and the ones I saw in DX Engineering were about $300 also. So that brings me to the purpose of this video. Is I have this little guy, and let's see, I also have this little guy, and I got them from Amazon. They just happened to show up one day I was browsing Amazon and kind of stumbled on these. And what they promise to do is measure RF output, of a radio. And sort of this is at a high level. The way it works is you have an input on this side, a little SMA coax input, and then you have an output on this side. And what comes out of the output is a voltage signal, and that corresponds to how much RF power it's seeing at the input. And this is just for powering it. And so to make that a little bit more concrete, what you may be able to do is, take your radio, and then with the proper cable and adapter, connect it up to this board, and then make your radio transmit. So maybe you send a message, or log into the admin page of, maybe this is a repeater, you log into the admin page, you ping it, you do whatever to make it transmit, and then you observe the voltage level coming out of this side, and maybe you see, oh, the voltage coming out is 1 volt or 2 volts, and that tells you how much power the radio is producing. So maybe 1 volt means that it's producing like half a watt, and maybe 2 volts means it's producing a full watt or something like that. We'll figure this all out together. That's what we're doing today. We're gonna do a little bench work, a little investigatory work to figure out if these actually do what they promise, because these were only $13. Each of these boards was only $13. And I'm gonna try to see if I can make this work with, other low-cost tools, just like, a common handheld multimeter. So we will learn together, and let's get started. Okay, so the first test that I want to perform on these boards is I want to know whether it's even safe to actually transmit into the RF input on these boards. And these are not evaluation boards that are made by Analog Devices, by the chip manufacturer. They're knockoff evaluation boards that I bought on Amazon, so I really have to treat them as an unknown quantity. And what I'm concerned about is I want to make sure that the inputs here actually present a 50 ohm load to the radio. So this is the same reason that your transmission line and your antenna need to be 50 ohms, because if there's an impedance mismatch, then the energy that you send down the transmission line or into the antenna will get reflected back at the transmitter and damage it. And this is exactly why, if you turn on the radio with the antenna disconnected, an open circuit. It's basically the two sides of the radio connection aren't connected through the antenna anymore, and you get all of the you get all of the power reflected back at you, and that's what can damage the transmitter. So to test this, I'm going to use my Nano VNA. This is a vector network analyzer, if you're not familiar, but basically it can do this measurement that I want. I want to know, at the transmission frequency, so at 900 megahertz, do these inputs present, a 50 ohm load to this device? And we can go ahead and see, just to get a little bit of get the lay of the land here, if you're unfamiliar. Right now, this is sweeping from 10 megahertz to 1 gigahertz, so it's generating a 10 megahertz signal, and then an 11 megahertz and a 12 megahertz and so on. It's sweeping up from 10 megahertz up to 1 gigahertz, and then it's measuring the power that's reflected, back down this coax, this transmission line. And with nothing connected to it, this is like this scenario where you've forgotten to connect the antenna to your transmitter. We can go ahead and see what's going on here. So remember, so frequency along the horizontal axis, and then the things we're measuring along the vertical axis. So we can see, let's go ahead and zoom in a little bit. We can see that the log magnitude, which is the ratio of the reflected power to the transmitted power, is 0 dB. And it's 0 dB across the entire sweep, across from 10 megahertz up to 1 gigahertz. And that's what we expect, right? All the power that's reflected is the same as the power that's sent. So we expect to see a ratio there of 0 dB. And the VSWR is really just the other side of the same coin. And what we see is that it's infinity. What we want to see when we attach the board is we want to see the log mag be some like negative value, like negative 30 or something, and we want to see the SWR be close to 1. And so if we attach a dummy load here, this is a 50 ohm dummy load. It's basically an SMA connector with a little 50 ohm resistor inside of it. And we can go ahead and connect it up to so I connected it up there onto the end of our coax. And now we can see that the yellow trace is the log magnitude. We can see it's now, some very negative value. So, at around 400 megahertz, it's negative 51, 52, it's moving a little bit. So that's great. That means that the reflected power is very, very small compared to the sent power. And then, similarly, the VSWR is, very close to 1. And what you'll notice here is that, the impedance varies with the frequency. So this is why, you can't attach a 100 megahertz antenna to your 900 megahertz LoRa transmitter, because the impedance at 900 megahertz might not be 50 ohms, even if it was designed for 50 ohms at 100 megahertz. So let's go ahead and do the measurement. So I'm going to go ahead and attach it here to this board, and we're going to see what we see. So, okay, so it's attached, and what we see is, I'm going to go ahead and move the marker here over to 910 megahertz, which is, the ISM band here in the US. If you're in Europe or the UK, you want to look over here more at 800 megahertz, but anyway, it looks like so the log magnitude is negative 9 dB down, and the VSWR is 2. So that's not great. A VSWR of 2 probably won't damage your transmitter, but the other reason why this is not great is because the way the log amplifier chip on the board works is it's measuring the voltage, and if the impedance isn't correct, it's going to measure the wrong voltage. So, two reasons this turns out this board is kind of junk. So this will probably go into the junk bin. But, one, it's reflecting a fair bit of power back at the transmitter, probably not a dangerous amount. And two, it's probably going to get the wrong reading. And actually, this was after I made some modifications to it. So I removed a capacitor here, and I removed an inductor here. And before I did that, the readings here were even more wacky. I think maybe they were trying to set up a balun here, which would actually be the right thing to do, because there's a differential input here, and we're going into coax here, which is unbalanced. So a balun would actually be the right thing to do, but however they did it, it's not working very well. So I tried to remove it, and it improved it, but it's still not great. Okay, you might say, well, but this is supposed to be for 600 megahertz, so we can go back down to 600 megahertz, and it does look much better there. So where am I at 300? So to be fair, it does look better there. So a VSWR of 1.6, and a log mag of negative 12 dB. But this was only after I made the modifications. Before I made them, this was all very wacky looking. So I would not buy this board. We'll probably stop looking at this now. And now we'll take a look at the other one. Hopefully this one's better. Oh, and if you're wondering, well, maybe it's the wrong impedance because it's not powered up. I did do it. I tested it with it powered on, and I got the same result. So, yeah. So let's connect up the other one here. All right. So now it's connected, and we can see this is looking much better, right? So let me go ahead and move the marker back up to 910 megahertz. There we go. And we can see, the SWR is 1.16 maybe, and the log mag is, negative 22 dB. So those are, those are pretty good for 900 megahertz. I think that's fine. So we can go ahead and continue to try to use this device, and we'll throw the other one in the junk bin. Okay, so for the next experiment, what I want to do is I want to feed a signal with a known power level into the board and then measure the output on the voltage side here. So I have this whole experiment set up. I have my tiny SA, which is not only a spectrum analyzer, but it also has a mode to be a signal generator. So I can, over here in this interface, I can program the frequency. So right now it's set to 915 megahertz, and the level. So this is set to negative 20 dBm, and this is for a 50 ohm load. And then I can, so at this frequency level, it has to be a square wave. It can't generate a sine wave at this level, but it should be close enough. And then I can go ahead and turn it on, and it will, output that 815 megahertz square wave out this port, and it'll be fed into this board. And then on the other side here, I have the voltage output connected to my multimeter here. I have this convenient little adapter that converts SMA to banana plug. You don't need this, strictly speaking. You could just touch your multimeter probes to, to here, or you could tack a little wire on there with some solder. Up to you. This adapter is incredibly cheap. I got it off Amazon. I got a whole bag of them off Amazon with different types for like $20 or something. I wouldn't trust it for any really sensitive measurement, but for this it's totally fine. I mean, you don't really need coax, right? This is not even an AC signal. So just wires tacked on there would work just fine. And then I have the power here. I have my bench power supply set to 8 volts. Heads up, when I got this, the wires were actually reversed here. So the black wire was going to VCC and the red wire was going to ground. So I fixed that now, but the first time I plugged it in backwards. I basically attached it in reverse, and thank goodness there's a protection diode here, because that saved my bacon. And it looks like there's also a voltage regulator here, but that's pretty much the setup here. So let me go ahead and plug the other side of this power cable in to my power supply off camera and see what happens. Set to 8 volts, drawing about 70 milliamps. Seems fine. And look, the light turned on, so we're in business here. We'll go ahead and turn on the DC volts here, getting about 2 volts out of the board right now with nothing being fed into it. So let's go ahead and turn it on. Yeah, this really only goes up to about negative 20 dBm. So we're going to go ahead and start with negative 20 dBm, and we'll turn the signal on here, and we're getting about 1.1. We'll round up 1.1 volts or 1.099. And so we can go and look at our data sheet here, and we're at negative 20 dBm right here. And if we follow the line up, we can see that it intersects this curve at, there you go, 1.1 volts. So that's right on the money. That's right on the money. Not bad. So then this is the highest level we can set it to. Maybe we can go down to like negative 30 dBm. The voltage out is about 1.35. So at negative 30, it is, there you go. Yeah, it's about 1.35, not bad. And then, this curve goes all the way down to, it looks like, it's linear up to, you have this nice linear curve all the way up to, almost negative 60, negative 55. Let's try negative 55 and see what happens there. This is a very tiny signal. And it looks like we have 1.95 volts now. 1.99 is jumping around a little bit, I think, because the signal is so incredibly weak. It's hard to measure negative 55 dBm. So let's see here. It is, there you go. I'd say that's, between, I'd say that's about 1.99. So right on the money, not bad, not bad. So I haven't been able to test the range above negative 20, but below negative 20, this is looking great. So I think what we can do is the next test will actually connect this to the radio and see if we can, capture the output on the multimeter here. Okay, so now for this experiment, I want to actually connect a real LoRa radio here to the board, and I want to see if I can catch the transmission on just one of my cheap handheld multimeters here. And I think what's going to be tricky here is these multimeters, they don't update very fast. So if the update rate of the reading is too low, we might not be able to catch the transmission from the radio here. But yeah, let's talk a little bit about the setup. So right here I have the rack 1 watt kit. I have it powered just from a lithium LiPo battery, just to make things easier, so I don't have any more power supplies and test leads tangled around here. And then I have this connected up to, let me move this over here. I have this connected up to, an IPEX to SMA, and then the SMA goes here. And this is a little bit different. I have these two attenuators here. So this is a 20 dB attenuator and a 10 dB attenuator. And when you stack them, they just add. So it's a total of 30 dB of attenuation. And the reason for that is that this, should output 30 dBm. But if we look at the chart here, the chart kind of caps out at about 10 dBm, and really it sort of flattens out even before that. So ideally we want to be on this linear part of the curve here. So if I have 30 dB of attenuation, then I should measure 0 dB at full power. So we should see, a little bit above 0.6 volts if this is working. And these, these are pretty inexpensive. You can buy lab grade ones that are very expensive, but I got a set of these off Amazon for I think $20 or $30, and they work surprisingly well. I measured it with my nano VNA, and the attenuation is flat across 0 to 1 gigahertz, so pretty good. This is not some super expensive lab equipment that you need for this. And that's good, right? Because I want this all to work with cheap stuff. That's kind of the whole point. Anyway, so this this feeds into my multimeter just like before, and I have the leads here. And I will go ahead and connect the power. We should see the light turn on. Okay, so we see the light turn on, and here we have, I'll move this over so you can see this better. That's reading 2.1 volts, which is kind of the no signal voltage. And now I'm going to come over here and I'm going to log into the repeater. This is just like a meshcore repeater. I'm going to log into it, and that'll trigger a transmission. So let me log in and see what we get. Oh, okay, so that was 0.6 something, I think, right? It flashed really fast, right? This is the problem with this, with using a multimeter like this, which doesn't have a min hold feature. Let me try again. Okay, so 0.6 something. You might have to, you might have to like record it and then go back and check the footage. Okay, 0.62, I think. If that was 0.62, then that's right on the money, right? It should have been, for 0 dBm, 30 minus 30 is 0. So it should be just a little bit north of 0.6 volts. So that's pretty good. It seems like this setup is working pretty well. The only thing is you have to really be watching this. And just a quick note, when I log into this, I'm logging into it even though there's no antenna attached to this, which is kind of interesting. LoRa is magic. It can pick up such small signals that it's picking up my companion, even though there's not actually an antenna attached to this radio. But that's cool. That feels like a success. If you have a nicer multimeter, then we can go ahead and try this with like a min hold feature over here. So here's a very expensive multimeter. You definitely don't need one this expensive, but this one does have a min hold feature on it. And so it's a little bit hard to see with all the glare, but we can see it will basically take measurements fairly fast. I have to go look in the manual for exactly how fast, and it will basically measure the max and the min and the average. So what we need to do first is we're going to go ahead and restart this. And then let's go ahead and log into the repeater again. And there you go, 0.608. So that's right on the money. That's a little bit more than 30 dB, according to this. I don't know if, we can tell. You probably can't tell the difference between like 31 dB and, 30 dB with this sort of thing. But that's great. That's great. This is working, right? So if you want to spend a little bit more money, you can get a multimeter with a min hold feature. It does not need to be a fancy fluke like this. I'm pretty sure X-Tech makes, maybe for 100, 150 bucks, you can get a nice multimeter with a min hold feature. So cool. This seems like a success. This seems like this is working. I think that's all the experiments I want to run. All right, so what did we learn today? I think what we learned is that this little board right here, okay, it's still connected. Let me disconnect it. This little board here I got for 13 bucks off Amazon actually makes a pretty decent power meter. If you only need to measure 1 watt. So what you need for this is you need the board, of course, and you need a multimeter, preferably one that updates quickly, or one with a min hold feature. And then to measure a watt, you need this set of attenuators. And I will go ahead and put a link in the description to all of these different products. But I think the set of attenuators was, I want to say it was $30. I'll double check on that. And the board was $13. And I'm kind of assuming you have a multimeter already. If you don't, then that a quality multimeter is probably going to be at least $50, maybe more like $100. But if you have those tools, you don't need, at least for this application, you don't need a spectrum analyzer. You don't need a dedicated watt meter. Those cost $200-300. So yeah, this seems like a success. I'm quite pleased with this outcome. Why might you want to spend more money? If you want to, so if you have higher power radios, right? This this little board, according to the data sheet, tops out at maybe 5 dBm. So if you have much higher power radios, a 5 watt radio, a 100 watt radio, this is probably not the right way to do it. You could get a giant attenuator and try to use that, but maybe in that case it would be more convenient to just buy an actual dedicated watt meter that can handle those power levels. But yeah, for you just want to make sure that you didn't accidentally burn out your radio, or maybe you have one of these 1 watt racks and you want to make sure that you're getting the full output, because if you power it incorrectly or set the jumper wrong or blah blah blah, then you get much worse output, much lower level output. But if you're sort of close to it, it appears to be working because it's still transmitting, just at a much lower level. And you don't really realize it's broken until you've put it on your roof or something, and you have to go back up there and take it down. So yeah, I think this is a success. I will post a link to all these different things in the description, and thanks for watching. All right, so it's the next day. I'm editing the video and I made a mistake. So the bottom line up front is that I think I overstated the accuracy of the board. So I think the board is off by about 3 dB, which means that if the board is telling you that the power level is negative 23 dBm, then the actual power level is closer to negative 20 dBm. So that's sort of the bottom line. I don't think it changes the conclusion of the video, which is why I'm not reshooting the entire thing. I think that, it's still good enough to tell whether or not your transmitter has been completely fried. But if you're interested in the minutia and you want to go further down the rabbit hole with me, then please stick around. If not, go ahead and close the tab. I totally understand. You just want to take the measurements and not worry about all of the little nitty gritty details. But I think if you're into that sort of thing, I think you might find this interesting. So okay, so what was the mistake I made? So when I was taking the measurements and referring to this graph in the datasheet on page 1 of the datasheet, and I'll put this in the video so you don't have to squint at this thing. If you look at the bottom, the graph says that it's the mapping between power level and voltage at 5.8 gigahertz, which is obviously wrong. We were using I was using 900 megahertz, 915 megahertz in the video. So now if you go over to let's see, page 8 of the datasheet, there's another graph. I'll put it in the video, and that the curve is shifted slightly, and there's a table in the front of the data sheet which tells you the slope and intercept of what the curve is for different values, so for different frequency ranges. So the question is, I think, what are the various sources of error? And this morning I went through a bunch of different possibilities and tried to rule some out. Really being 100% sure about what's contributing and what's not, I think would be a ton of work, but I tried to filter through them. So, the first possible source of error is that this device is really calibrated for sine waves, and I was using a square wave in the generator. And, so if you have a sine wave at 900 megahertz, all of the power is concentrated in that slice of the spectrum. But if you have a square wave that's 900 megahertz, then there's actually all of these higher frequency components that make up that square wave. And if your measurement device is sensitive to that, it expects a sine wave, and you're going to get a different value than what you expect. So I did some research on this, tried to do some math, and I think this doesn't really explain the error. I also did an experiment with my signal generator where I generated both the sine and square wave, and the error was maybe a dB or something like that. So I don't think that fully explains the problem, but maybe it's a contributing factor. Another source of error is that my signal generator has an accuracy of plus or minus 1 dB in the generated signal. So maybe when I programmed it to, when I set it to generate a 20 dBm signal, maybe it's actually generating a 21 or negative 20 dBm signal, then maybe it's actually generating a negative 19 or negative 21 power level there. So that could be another dB that's explained. But I think probably the biggest source of error is just that in the data sheet it says that from IC, from chip to chip, there can be manufacturing differences that cause plus or minus 2 dB. And the way I know that is in the table, it will tell you the slope and intercept of the curve, right? So I'll put this in the video. It tells you the slope and intercept, and it tells you that the intercept of that curve can vary by plus or minus 2, which would result in a plus or minus 2 dB change, and then the intercept can also the slope can also change. So what the manufacturer recommends is that every board should have a 2-point calibration, right? You should take two measurements. You should take two measurements from a source that generates a frequency of known power, or a signal of known power, and then you should be able to calibrate that curve using those 2 points. You can calculate the slope and the intercept from those 2 points, and that kind of matches what I showed in the video, which is that that 3 dB error was pretty consistent across all the measurements I did. So if you can put a signal of known power into there, and then or preferably two different signals of known power, then you can calibrate the curve for that frequency. So you can do that at home, right? You can take if you have a device that outputs a known power level, then you can try to use that to calibrate the curve. So maybe you have one transmitter that outputs, supposed to output around, supposed to output around 20 dBm. Then you can use that to figure out what the error is, and you can also like change the power level on these LoRa transmitters. So you can do that. I guess the problem with that is that now it's adding one more thing to your one more tool that you need to actually use this board. So it makes it a little bit less appealing, and it's unclear if how well calibrated the power level is of whatever device you're using to calibrate it. So I think maybe what you do is you just accept that you might be off by a bit, but as long as the measured value is close to what you expect it to be, then things are probably fine. I guess this is the drawback of trying to do this on a shoestring, right? If you feel like that's way too much trouble and you'd rather just spend money to solve the problem, totally valid thing to do, then you can go and just buy a RF power meter that's designed to do this and has a spec sheet that tells you exactly what they expect the error to be. But if you kind of want to do this on a shoestring, or you think it's interesting, I obviously find this stuff interesting. I think it's kind of fun. I'm probably going to go and actually, well, I already did this. I already went and calculated the new slope and intercept for my board. But if that's not fun for you, then it totally makes sense just to spend more money to solve the problem. But anyway, so that is my correction. Hopefully it didn't change the outcome too much. I don't think it really did. I think it's still an interesting tool to have if you want to try to do some diagnostics on power level on a shoestring budget. And yeah, all right. Well, thank you for watching.